car earlier, and all of a sudden water just starts spewing on the bottom of my water bottle. I don't know what I hit it on.
And now it's recorded.
I don't care.
Okay. All right, so you still have a fair amount of time to do. Okay. I guess I have to keep a real close eye on this thing when filming or recording aborts. Okay. So as I was saying before it cut off, you have plenty of time for the next homework, but you still can't do all of the problems just yet.
That's why.
The very last problem cannot be done.
Hello.
Until I cover that stuff,
I dare you to do it. I dare you to go
which
in
will
there.
be on Monday.
How can we start working on it?
Well, don't start the last problem.
I told him he should. I dared him.
Everything
to do
else has been covered and is doable, as Candace will soon find out. So, okay. Well, I mean, you guys will find out later because she always starts first. Okay. Now I just have a few pages of notes to get through. All right. So these are the most interesting and also most troublesome kind of first-order equations. Okay. Now, so I want to warn you going in. This is not going to be easy stuff to digest just because the way we go about constructing solutions when we can is a bit unusual. We're dealing with solutions that have discontinuities in them, and that complicates the whole picture. It's still method of characteristics, that part is the same, but I'll do my best to try to explain how we actually can construct explicit solutions in spite of these discontinuities. Okay, so the kind of PDE we're going to solve in this case is a general form of conservation law. So udt plus ddx of some general function f of u is 0. But for purpose of applying method characteristics, I'm going to rewrite it by carrying out the differentiation. So if I carry out the differentiation with respect to x, I use a chain rule. So I'm going to get f prime of u, but I'm going to call that g of u. So g is f prime, times du dx. So it's a straight chain rule here. So this is the form we'll work with as far as definite characteristics is concerned. And then we'll throw an initial condition, u of x0 equals h of x. So then we proceed in exactly the same way as before to try to get a solution. So our characteristic equations, so dx d tau is equal to this coefficient g of u, and we'll evaluate u at tau s. Okay. And then our initial value is from our initial curve, which is just the x-axis. Okay. Oh, so that'll be s. Okay, good, still recording. All right, dt d tau. So the textbook uses y as their time variable. Y, I don't know. That was not an intentional pun, I swear. Okay, dt d tau is this coefficient, which is just going to be 1. And its initial value will be 0, because we're on the x-axis. And finally, du d tau is this coefficient over here, but that's 0. And its initial value is going to be from the initial condition, h of s. Okay, so this is slightly different than Definite characteristics for linear problems. When you're using solving a linear problem using definite characteristics, you solve your x and t equations or your x and y equations first, and then you solve this one. Here we have to go about it in a different order. So, first, go ahead and solve your t equation. That's no problem. So what's t going to be?
Just.
Yeah, t is going to be tau. All right. The next equation to solve is actually your u equation. What is your u equation going to be?
So then h of s.
Yeah, because it doesn't change at all. It's just equal to the initial value. Okay, so that's no problem. Yeah.
The tau of 0s equals 0. Is it going to be t of 0s in the second one?
Yeah, it should be t. Okay. All right. Because if you look back at your x equation, we have dx d tau is g of u tau s. And that's bad, because this makes it look like it's a non-autonomous ODE. That's going to be a lot harder to solve. Except for one thing, u doesn't actually depend on tau. It only depends on s. So I can rewrite my x equation now. X tau is equal to g of u is just equal to h of s. And we have the same initial condition. So now, this is a simple ODE to solve because there's no dependence on tau on the right side. So what is x going to be equal to?
Well, g of hs times tau plus s.
Yeah. Okay, so as long as you solve equations in the right order, they actually are all easy to solve. Okay. Now we can put everything together. We have, because we want our solution u of x and t is going to be h of s, which is x minus g, but this is u, minus g of u tau, but tau is t. So this is at least an implicit form. We have our solution. You've seen things like this in certain homework problems. Okay. So generally it's not possible to rewrite this in order to say u equals something, but in certain cases you can. Okay.
Where do you get the h from?
From down here.
Okay, u equals h of s, and
Yeah,
s
and we
itself is... Okay, right.
Yeah. Okay. Any other question? Okay. So producing a solution wasn't very difficult, but now it's understanding how the solution behaves. That's where things get a lot more interesting and strange. Okay. So I guess for posterity I can say that this is a day when the world is sad that neither Chris Christie nor Carly Fiorina will be our president.
Right.
So sad. You just said it so fast. I heard,
But then
like,
there's still that guy. Who is,
Yeah, but that neither Chris Christie nor Carly Fiorina will be our president because they both dropped out of a race today.
I just heard like Chris, and I'm like, what?
Anyhow, okay. So to understand how the solution behaves, since we don't have an explicit formula for it, we need to look at our characteristics. So these are the curves just in the xt plane. So we have x is equal to, so instead of s, I'm going to use x naught as like a specific x value, because here's our x-axis. Over there, I was using s as a parameter along the initial curve, the x-axis. But now I'm using x naught. plus g of h of x naught. I'm changing notation just to reinforce the notion that our initial point of our characteristic curve is an x value, so you can interpret it like that. Okay. So if I were to draw these characteristic curves, they're starting at a point x naught, and then they're straight lines. Now, based on, keep in mind this is a xt plane, so t is playing a role of y. So the characteristics are straight lines, and a slope, that is change in t over change of x. That's the slope for graphing purposes. But here I have x as a function of t, not the other way around. So the slope is not g. The slope is actually 1 over g. Okay. All right.
Why is that?
Well, because normally when you think of lines, you have like y equals mx plus b. But here I have, that's y as a function of x. This is x as a function of y, of t. So in order to get this, so I could rewrite this as
T equals, right.
x minus x naught over that. And then it's in the standard form, or something more like that.
Right.
Okay. All right. But here's the thing. Notice the slope depends on x. So in fact, I only get this kind of picture if h is independent of x, but generally it's not. You can have different slopes. So we could have a situation like this, where maybe the slopes get smaller, so the characteristics start diverging. Or I could have a situation like this, where maybe the characteristics will converge on one another. We could have a situation like this. So either one of these can happen. Now, actually I'm going to draw, so when you have something like this, where the characteristics they spread out. So this kind of thing is happening where they start going off in different directions and they will not intersect. That is called an expansion wave. Okay. Whereas over here, we have the characteristics changing slope in such a way that they might collide with one another. So like these, if I were to keep going, these would eventually meet at some point. So in this case, so that's called a compression wave. Now, here's a problem in this situation. Each of these have different initial values coming from h of s, and they're being propagated along these curves, but they're all different. So if these characteristics collide, that means the solution is trying to assume multiple values at once. So that is called a shock. It's basically a terrible situation mathematically, because now you're not sure how your solution is defined anymore. And you have to try to make sense of how your solution is going to behave once that collision happens. This situation is nice, that your solution remains continuous. There's never any conflict among values. In fact, well, you might actually get some non-uniqueness in these cases. But this is just a big mess. And that's the mess we're focusing on today. Okay. So in this case, well, before we try to figure out when this intersection might happen, if it's going to happen, let's take a look at these two situations, these two pictures. Because in this case, when the slopes are spreading out, how is the slope changing? from as I go from left to right.
Oh, it's decreasing, right?
Yes, the slope is decreasing.
Which means g is greater than 1.
Well, no, not necessarily, but the point is, as x naught increases,
That function.
yeah, so the slope is decreasing. So but when the slope is decreasing, the slope is 1 over g. So that means that g is increasing. Okay. As a function of x naught. All right. So, as you can imagine, the opposite situation is happening here. What's happening here is, as we go from left to right, the slope is getting steeper, and that's allowing this collision to happen. So g of h of x naught is decreasing. Okay. Now, so now the question we can answer is, when do the characteristics intersect? Because that's when we know we have a problem. Okay. So the way that you can do that is we can actually take a look at du dx. So we have u is equal to h of x minus g of u t. So now I can differentiate this, both sides, with respect to x. So I have ux is equal to h prime of all this, times the derivative of what's inside. Well, that's going to be 1 minus g prime of u du dx times t. So from my implicit form of u, I now have an implicit form of du dx. However, now what I can do is I can go ahead and rearrange this and solve for du dx. You did something similar in homework 1, actually. So by taking like this term with ux and moving it to the other side and rearranging, what you get is ux is equal to h prime of what's in here, but this, remember what's in here from the other board has to equal to s, so I'll just abbreviate it as s. So h prime of s over 1 plus h prime of s g prime of u times t. Okay. All right. Now, now the thing is, we're going to have a problem if du dx should go infinite. Because what happens is, at some point, if the slope keeps getting steeper, eventually it's going to go vertical. And that's when you have a discontinuity solution. So, in other words, when its denominator is 0. So I can go ahead and just set this denominator equal to 0 and solve for t. So t sub c, which is like a critical time, is minus 1 over g prime of u, h prime of s. Okay.
I'm sorry, what part are you saying is equal to s in there? Just the g of u or the whole thing?
Yes.
Okay.
Yeah, but you see it from previous board.
Oh. That's
Because I have h of s.
oh, okay.
Yeah.
Sorry.
Okay. All right. Now, if I keep in mind, though, that in here, u is h of s. So I can write this as 1 over d ds, with respect to s, g of h of s. Okay. So I can condense it like that. Okay. Now, and this comes from U equals H of S by plugging that in there. You're just undoing the chain rule. So, I care about what's happening for positive time. So, in order to have a positive time where these characteristics intersect, well, my critical time is minus 1 over this. Therefore, I need this denominator here to be negative. What does that mean? That means g of h is decreasing. So, in other words, derivative of this has to be negative. So these two situations are consistent. The difference is now we have a specific time value where things go wrong. I sense a puzzle.
I'm trying to figure out is G H of S? That's what, or what do you
Well, okay, here I was using x for s,
Okay.
but g of h of whatever.
Okay.
That says T, that looks like C.
Yeah, critical time.
Okay.
Yeah.
Okay. Wow, C also.
Okay. All right. So,
We already knew that, so why did we sort of?
well, we knew that from here,
Right.
but this didn't tell us when. So the idea is, starting from t equals 0, everything's fine. You have a continuous solution, but at some point it breaks down. This told us under what circumstance it's going to break down, like if g of h of x is decreasing, but it didn't tell us when.
It's decreasing, starting from that time, that critical time.
Well, the thing is, as it's decreasing, that doesn't cause trouble to develop right away. In other words, it's basically conditions are right for it. But only when the time hits this level, that's when you actually have an intersection of characteristics where we meet together, where we all meet, and then you have a discontinuity. So I guess you could think of it in more practical terms, especially here in the South. Tornado warning, tornado is hit. So, yeah, in other words, sirens have gone off and you're done for at that time. So, okay. Let's see. All right. So here's a problem. PDEs like this are used to model physical phenomena, like traffic flow. In fact, this equation specifically, if you choose to write G, will model traffic flow for you. And we'll talk at the end about how to pick the right G. And the thing is, if you're modeling traffic flow, and what can happen is, your solution U represents the density of cars along the highway at any point x at any time t. So as a commute time and more cars are piling on, then your solution U is going to be increasing. So what happens is, like, once you have enough traffic, shocks can occur, and as I mentioned the situation before, where you have traffic moving along and all of a sudden seems to stop for no reason and then continue on. So basically there's discontinuity happening. And the thing is, whatever you're modeling doesn't care what happens to you mathematically, obviously. It's still, whatever phenomena is at work, it's still going through its natural process. And so we have to find a way, once this solution we've solved for over there, using limited characteristics, is no longer viable, we still have to construct a solution anyway that has the discontinuity in it. Okay. Fortunately, we can actually do that. Because we can look at the weak form of the equation, because a classical solution has to have all the required derivatives, like du dt and du dx. If you have a discontinuity, you don't have derivatives anymore. So we need to work around that, and the weak form of a PDE allows us to do that. Okay. Okay. So, work with the weak form. Okay. I'm going to integrate over some interval from a to b, an interval in x. And I'm going to use C or squiggly as a placeholder for x. Okay, so that's the first term of my equation there, and then I'll integrate the other term separately, where we have f of u. Okay, so all I've done here is I've just taken the PDE, this original form, and integrated over some interval AB in x. Oh, equals 0. Okay. Now, here I'm integrating a derivative, so that cancels out. So also here I have a derivative with respect to t, but I'm integrating with respect to x basically. So I can pull the time derivative out. Okay, so here because I'm integrating a derivative, I can just plug in the limits for x. So I have f of u of bt minus f of u of at, 0. Okay. Now, at each time, the discontinuity is going to occur at a different point in x. Because if you go back over here, what I had before, your critical time, is minus 1 over derivative of g of h of s, or g of h of x. In other words, each x leads to a different discontinuity time. So let's suppose a discontinuity. Let's suppose discontinuity occurs along a curve. X is some function gamma of t. Right. So if you want, you can think of for each fixed t, discontinuity occurs at a different x. Okay. So now what I can do is, if I pick an interval AB, wherever discontinuity occurs, I can take it into account in this equation here. So what I'm going to do is I'm going to break up this integral into 2. So I have integral from a to gamma of t, and then integral from gamma of t to b. Oh, that's not dt, it's dc. D squiggly. Equal, and then everything else. Okay. And I'm doing that because within each of these two separate integrals, u is continuous. So each of those individually, I can apply the fundamental theorem of calculus. And now what I can do is I can actually carry out the differentiation with respect to t. And this is where we get to the dark side of the fundamental theorem of calculus, if you will. Because notice I have two dependencies on t, here and here. I have to take both of them into account. So the way I do that is, first, we think of this as though we are differentiating an integral. So it cancels out. So you get u of, okay. So I need some new notation here. U minus times gamma prime. Now, the idea is, here we have a discontinuity in u. So here we have x equals gamma of t. The value of u on the left side, I'm calling u minus. The value of u on the right side, I'm calling u plus. Okay. So here we have u minus. So I'm going to have u minus times the derivative, because we have to use a chain rule for fundamental theory of calculus. And then, over here, I have the same thing going on. I'm differentiating the integral, but it's the lower limit this time. So I'm going to have a minus u plus, and then still gamma prime. Okay. So this comes about from differentiating the integrals. But now I have to take into account that u also depends on t. So I'm going to have plus the integral from a to gamma of t of du dt plus the integral from gamma of t to b of du dt. My squigglies are getting bad. Try to not let that happen. And then still this other stuff. Okay. All right. Now, if we go back to the PDE itself, the PDE is du dt plus ddx of f of u equals 0. But that means I can replace ut in here. So this is equal to minus derivative with respect to c of f of u. Okay. But the thing is, now what I'm doing is I'm integrating with respect to c a derivative with respect to c. So we cancel. So now what I'm going to get is, okay, so I still have u minus gamma prime minus u plus gamma prime. And then I'm going to have, and I use this in both these integrals, so I'm going to have minus big F of u minus, because this is from the upper limit. That's u of gamma of t, right? From the left side. And then I have minus a minus makes a plus, big F of u of at. Okay. So this comes from the first integral, from a to gamma of t. Then I have this again. Okay, so I have minus big F of u of bt. Minus a minus makes a plus, big F of u plus. and then I still have the other terms. Plus f of u of bt minus big F of u of at is 0. Okay. So all I did to get these 4 terms is I evaluated these 2 integrals by changing du dt to minus ddx. So any questions about that part of it? So the integral of ut is minus the integral of f of u, derivative with respect to c, but that is going to be minus f of u evaluated at whatever limits you have. Okay. So that's all I did here, and the thing is, u of gamma of t is the x value, because that's your discontinuity curve, is equal to u minus on the left and u plus on the right. So that's why I plug in u minus down here and u plus over here. Now, I can simplify some things. These cancel, and these cancel. So, now what I can do is I can rearrange all this and solve for gamma prime. So when I do that, I get gamma prime is equal to big F of u plus minus big F of u minus over u plus minus u minus. Okay. And this is called the Rankine-Hugoniot condition. Okay. What does it tell us? That's the important thing. Because this is gamma prime, so this is how the discontinuity point x is changing. So this is the speed at which the discontinuity propagates. Okay. In other words, once a discontinuity occurs, this tells us all we need to know about how the solution actually behaves from that time forward. Okay.
And f of u's are.
What?
I mean, u plus and u minus. Like, what roles do f of u plus in it?
Oh, because you have discontinuity happening.
Right.
So these are just the 2 values of f. It's a jump.
Right.
So it's what values you're jumping from and to.
Yeah, it looks like a derivative, right? F of
It does, yeah. So, okay. Yeah, and that comes, so basically, if you can, f is like your flux function, it's a derivative of flux with respect to your solution value, and that indicates how fast the.
But is the denominator go to 0?
No, actually, it never goes to 0 because it's a discontinuity. There's always a finite non-zero gap between 2 values.
U plus, u minus.
Yeah. Okay, now what I'm going to do is give an example where we can actually construct the solution both before the discontinuity happens and after. And you can see, I can draw graphs, and then you can see how the solution behaves both before and after the shock happens. Because the whole idea is we want to get something that's physically sensible. Because physically, something's happening no matter what, and before and after discontinuity. We just have to try to be able to make sense of it mathematically however we can. Okay. So for this example, we'll have, how am I doing on time? Okay, not bad. ut plus ux is 0. So in other words, my big F is 1/2 u squared, so g of u, which is f prime of u, is just going to be u. Okay. Now to best illustrate what's going on, I'm going to use a initial condition that is piecewise linear, but still continuous. And then we'll see how, although the solution starts out being continuous, eventually it becomes discontinuous. Okay, so the solution is, it starts out being 1 for negative x. And then I have the solution decrease to 0 over an interval of width alpha in a linear fashion. So once x becomes alpha, this whole expression becomes 0, and the solution remains 0 from that point on. So I look at the xu plane as opposed to the xt plane. It's a very important distinction. So first the solution is equal to 1, and then it decreases to 0 like this. All right, so this is my alpha right there. Okay. So I'm decreasing by 1 over an interval of length alpha, so my slope is minus 1 over alpha. Okay, so this is what's happening at t equals 0. Okay. Now, we already have a formula for solution. We do not need to do method of characteristics again, because we went through it in the general case the last time. So the solution, at least while it's continuous, is u equals h of x minus ut. All right. We just have to try to make sense of that, because we'd like to have an explicit formula if we can. Okay. Now, so for this, to figure out what's going on here, we need to use this formula. So what's happening is, when is this equal to 0, for instance? When this is negative. Oh, sorry, no, I goofed. This is equal to 1 when the argument is negative. So, of x minus ut is less than or equal to 0. But the thing is, this is also u. U is equal to 1, so I can plug that in here. So x minus t is less than or equal to 0, so it means that x is less than or equal to t. So it's equal to 1. So this situation, when t equals 0, becomes this situation. X is less than or equal to t. So I'm actually using the h, so I'm using u, the same u value on both sides of the equation. Okay. Now, what about when it's decreasing linearly? So that's the second situation. So u equals h of x minus ut is equal to 1 minus this value, whatever is plugged in to h. But in this case, that is x minus ut over alpha. And this holds whenever x minus ut is between 0 and alpha. Okay. So now I have u on both sides of the equation again. So I have u equals 1 minus x minus ut over alpha. And I have to solve that for u. So if we go ahead and do that, I have alpha u equals 1 minus x plus ut. So now I can move this over to the other side. So I get u equals, okay. Something seems,
But that would be
yeah, from here to here,
yeah.
transcribing mistake. Okay. Yes, now that's what I want.
Wait, you know what it's for? Oh, never mind.
Okay, so alpha minus x plus ut. And I'm rearrange everything quite a bit. But when I solve for u, I'm going to get x minus alpha over t minus alpha. Okay. And if I take this u value and substitute it into this condition, then what I end up getting is x is between t and alpha. Okay, so I can fill that in here. So it's x minus alpha over t minus alpha when x is between t and alpha. So when x is less or equal to t, it's equal to 1, and then what happens is it's from here, starting at 1, it's decreasing all the way down to 0. And so now I have this. If this is greater than or equal to alpha, u is equal to 0. But if u is 0, this term isn't even here.
X is greater than
Yes, x is greater or equal to alpha.
So we just replace t with zeros, right? I mean, sorry, zeros with t's from the first one.
Oh, well, if you were to backtrack from here to here, yeah.
Right.
Okay. All right. So the thing is, now what's going on? So if I draw the solution again, because notice, for all time, the solution is going to 0 at alpha. But what's happening is, the solution is equal to 1 for a longer time. And what is the slope? The slope is 1 over t minus alpha. But t is getting closer and closer to alpha. Therefore, the denominator is getting smaller. The slope is getting steeper and still negative. So it's going to behave something like this. And then it's just going to keep getting worse and worse. So it's going to be a sharper drop. But still going to 0 at this point. So if I let this keep evolving at this point, what's eventually going to happen?
Discontinuous.
Yeah, at some point.
You have a vertical.
Yeah, in fact, at what time is that going to happen?
T equals alpha.
At t equals alpha, because this interval is shrinking to nothing. So, all right, so this is between t between 0 and alpha. So now, when t equals alpha, we have a sharp jump discontinuity from 1 jumping down to 0. Okay. Okay. Now, actually, the critical time that we had before, the formula for TC is minus 1 over g prime of h of x naught. But in this case, g of u equals u. So g prime is just,
One.
yeah, oh wait, I missed one thing here. G prime of h of x, h prime. Okay, so we have, this part is just equal to 1. But what is h prime? H prime is minus 1 over alpha in this interval. So you sort all this out and you get minus 1 over alpha. It's alpha. So now that's what we can see from the pictures, but now we see from this formula too, it all behaves consistently. Okay. Any questions on how the solution is behaving? It's only because of the nice form of h being this piecewise defined and piecewise linear function that we're able to solve for a value of u in all three of these cases and figure out which behavior we're getting at what time. So for a more complicated h, we wouldn't be able to do that. But for some of these simple cases where you have like piecewise linear, piecewise constant data, you can figure out a lot about how solutions of the PDE behave. But then what? How does the solution behave after that? And that's where the ranking Hugonio condition comes into play. Okay. Whoa. Thank you for suggesting it. What?
Said you're still on my move.
Yes, but see, I'm not bleeding.
I tripped backwards over a chair day in class. I didn't fall, but I tripped.
That must have been amusing for your students.
They laughed.
Well, it's important to make your students laugh.
They always laugh, though. It's something.
Okay, so for t greater or equal to alpha, the ranking Hugonio condition, we apply that. We have gamma prime is f of u plus, which is equal to, 0 actually, minus f of u minus all over u plus, which is 0, minus u minus, because u minus is equal to 1, u plus is equal to 0. Now, f of u is 1/2 u squared. Okay. So once we sort all that out, we get 1/2. So what happens is, after t equals greater than alpha, the continuity keeps propagating at a speed of 1/2. So here's alpha. So for t greater than alpha, we get, so this discontinuity has moved on, and it just keeps going. So for this particular equation, it's just going to keep traveling in that direction, and knowing its speed is 1/2, that'll tell us exactly where along the x-axis it is.
How will the graph be like after each half times what?
Because it's so it's dx dt. So in other words, for every 1 unit of time, the discontinuity will move with 1/2 a unit in x.
Okay, so from say, okay, t equals alpha, if there's a discontinuity, if it goes alpha plus 1,
Yeah.
it would go to x whatever plus 1/2.
Right. Okay. All right. And in fact, actually what we can do is we can write down formulas for a solution that account for this discontinuity. So it would be equal to 1 as long as x is less than, so the dividing time will be alpha plus 1/2 t minus alpha. Because the change in t will be halved to indicate the change in x. Once you get past that point, then the solution jumps straight down to 0. Okay. So at first the solution is nice and continuous, piecewise linear. Then the characteristics are colliding, you get a compression wave. And you can see why it's called a compression wave, because the wave is compressing. And once you have a jump discontinuity from a wave becoming vertical, basically, then it just goes forward to the right at a constant speed. Okay. Now, let's see, how much time do I have? Okay, I can do this. Let's change the example a little bit. Same PDE, but a different initial condition. So what happens in this case, we're going to, instead of going from 1 to 0, we're going from 0 to 1. Because remember, we needed g of h of x to be decreasing to have a compression wave. Now, well, g of h is h in this case. So now g of h is increasing. That means we're going to get an expansion wave. Okay. So now we have x over alpha. So same kind of piecewise linear progression. So what happens is the solution behaves like, it starts at 0, jumps up to, actually goes up to 1 in a piecewise linear fashion. You might think, well, how different can the behavior be? Well, incredibly different. So what happens is the solution okay, so because u, it's the same situation, h of x minus ut. So you check, when is this less than or equal to 0? When that happens, u is 0. But then this term also is 0, because you plug in u equals 0 in both places. X less than or equal to t. No, 0. I don't know if you said...
Yeah, because t goes away.
Yeah.
Because u is 0, okay.
Yeah, because it's multiplied by u.
Right.
Okay, I'm not listening to you anymore.
Although he said something earlier that was right, and you were like, no, and then you said the exact same thing. And I was like, wait a second, huh?
Wait, I used what he said?
Yes.
But I said no?
Yeah, you said no, not exactly, and then what you said was exactly the same, and I'm like, wait, what?
Why don't you point those things out?
Well, I was kind of behind on the writing, and
I need to know that.
No.
Well, I wasn't sure if I heard him wrong, if I heard you wrong, but I was like, I thought, because you got that face like,
No,
wait.
I may have, had not a right idea.
No, because what if I read something wrong?
well, I thought maybe you heard him wrong or something, I don't know.
Okay. I can't let stuff like that slide, so point it out.
Wait, okay, what's the question mark?
Okay, so t disappears because it's multiplied by
U, which is 0.
Yeah.
Why does it have a question
Got it.
mark? Okay.
Okay. All right. It's too late in the day for this. Okay. Now for the second situation, u is equal to, okay, so h is going to be x over alpha. So u is x over alpha. Okay, let me make sure this is similar to what I had before. Well, actually, I'm just going to leave it as u. U is equal to h of x minus ut, which is equal to this, x minus ut over alpha. So now what I would do in this case is I go ahead and solve for u. So alpha u is equal to x minus ut. So alpha u plus ut is equal to x. So u is equal to x over alpha plus t. So that's my solution value in this case. And you can see it's consistent with that at t equals 0. Alpha plus t. And this is for the interval, so as long as x minus ut is greater than 0 and greater than alpha, okay, but the thing is, u is equal to this, so I need to plug this in here. So once I sort all that out, I get x is greater than 0, less than t plus alpha. Okay. So that's my second interval. And then finally, it moves up to 1 when, okay, so third situation, we get u is equal to 1 if x minus ut is greater than or equal to alpha. But u is equal to 1. So x minus t is greater than or equal to alpha. So x is greater than or equal to alpha plus t plus alpha. Okay, so that's what's happening in this case. So in all three situations, you're checking, you're filling in x minus ut for x in here to figure out what u is going to be and also when that situation applies. Right, so it all comes from x minus ut playing the role of x in your initial condition. Okay. Now, how does the solution behave? You want to do the same thing as before, graph it. Now, the so what happens in this case, our critical time is minus 1 over g prime times h prime, but g prime is still 1. H prime is 1 over alpha. So it's negative. That means there is no critical time. We only care about what happens when t is positive.
So does that mean like x naught? So x naught over here was alpha, right? And that's fixed. So over here x naught would constantly move, right?
Well, the thing is, x naught ends up being irrelevant just because h is a linear function. So the derivative is constant anyway.
Okay. So I guess what I'm asking is over here, alpha alpha's not moving at all.
The alpha is a fixed constant.
Alpha's fixed, but over here
Alpha is still fixed.
But the interval is attached to alpha plus t, right?
Yeah, well, you'll see what that means when I draw the solution.
Okay.
Yeah, so alpha is always fixed. And
The negative alpha is still alpha because,
well, the point is, if there is a critical time at all, it's going to be negative. But I mean, but we're only
there is no negative time, so there is not going to be a critical time.
right.
So we could just
Yeah.
ignore it.
Yeah, so what's going to happen is the solution is always going to be continuous. And you can see, if you were to graph it, okay, so we have the initial condition, goes from 0 and it moves up to, actually, for benefit of the people watching at home, I'll redraw it over here. Okay, then we have, okay, so we have alpha in the same place in both cases. Okay. So at first, it starts out at 0, increases up to 1. All right. Now, it starts at 0, and it's still going to increase, but notice the slope is 1 over t plus alpha. Because of that plus t being thrown in there, the slope is less. So it's decreasing, so sorry, the slope is decreasing. The solution is still increasing and will still hit 1, but it hits it later. So the solution is going to give the appearance of like flattening out. So as t progresses, it's going to take even longer. So instead of a wave contracting, like collapsing onto itself, like in the previous example, the wave is expanding. That's why we call it an expansion wave. So the solution is going to remain continuous for all time. Okay, so that's why it's important that g of h of s is a decreasing function of s in order to have a shock. Otherwise, the solution will always be continuous. Okay. But the thing is, what you can also have happen in the case of an expansion wave is that your solution, here, this is a classical solution that has required derivatives. If we have if you look at the weak form of a solution, like I did before, for a general case, we may actually get more than one weak solution. So, in order to make sure we have a unique solution, in all cases, okay, all right. You have to satisfy what's called the entropy condition. So f prime at u minus is greater than gamma prime, which is greater than f prime of u plus. But the thing is, by the Rankine-Hugoniot condition, that is equal to the average rate of change between u minus and u plus. Okay. But the point is, the instantaneous rate of change at u minus must be the greater of the two. So another way of putting it is the exact condition that I had earlier. G equals f prime is decreasing. If this doesn't hold, what happens is a weak solution is not unique, and you should use a classical solution instead. But it's going to remain continuous. So this is a case of an expansion wave. It's when this entropy condition does hold, is when you're going to develop a shock. So then the compression wave that the weak solution gives you is going to be the solution that you want.
Are those intentional? Like that says f prime of u minus is greater than blah blah. Are those not supposed to be primes? On the definition of gamma is. Oh well, they're not over here. Never mind. I guess not.
Right. Okay.
Never mind.
Okay.
So you're saying to satisfy the entropy condition, so G equals F prime has to be decreasing, meaning the instantaneous change. I get all that.
Okay.
Then the weak solution is unique.
Because that's the only solution you're going to have.
Right.
Because when this does not hold, you can still get a classical solution, and you can get a weak solution. Because if you have a classical solution, you can always get a weak solution too, but not necessarily the other way around. And generally, both should agree for most part. But the thing is, when this is not satisfied, you may get a weak solution that is altogether different. But that's not the solution you want.
Right. Would that involve like having a shock?
It won't. When this doesn't hold, no solutions will have a discontinuity in them. They'll just achieve continuity in a different way.
Okay.
And because the thing is, The entropy condition is based on physical considerations. So another way of describing this in words is any characteristics that you have can only enter a shock curve. And by shock curve, I mean gamma t.
Is it the same argument for Hawking? Like
What?
information can get in the black hole.
Yeah, well, yeah, information can only be lost.
Okay, lost and not like retained. I think they're talking about something. Anyways, but
Yeah.
is that
Yeah, because characteristics colliding with each other at a single point that causes discontinuity, that's information loss. You can't have a situation where you have a shock curve and you have new characteristics sprouting from it. It's like you're creating information. Physically, that doesn't make any sense. So that's why we need solutions to satisfy the entropy condition if you're going to have a shock curve at all. Otherwise, physically, that's not sensible. Okay. Oh, I'm 2 minutes past. Okay, but I'm done. So, all right, so we'll finish off this chapter on Monday.